Today we have two lectures. One, first of them just now, and the second one at 4. So today something about field phenomena.
Yeah, partly. Yeah.
So Ingemar Kaj from Uppsala will speak about fractional Poisson motion. So you're welcome.
Thank you. Yes, this topic I would like to talk about is its origin about 15 years ago. This type of result and this type of models I would like to talk about, in particular by a paper of in a paper by Taku and others, co-workers, and it was driven at that time largely by an effort to response to measurements of network traffic data at the time. And this seems to be a topic that has been going on. People keep measuring things, and there is some rather persistent pattern in these reported measurements that you see a lot of particular data characteristics that indicate this sort of heavy tails and the cell similarity and all that. So I will generally speaking, talk to that subject, but not so much about measurements in themselves. But a little bit on the origin, possible origin of these mechanisms, and look at possibilities that our short tail models that we like so much can maybe generate somehow intrinsically also this type of strong dependencies that we see. A particular model I would like to discuss is it's called randomized service, or the possibility that by randomizing the service rates you can actually and thereby have correlation between jobs or users, that you can see some effects of that. So this will be one part in the first half or so about a particular model that I hope is new and that I would like to present. I don't have much results to present, but at least I'll discuss the model. And then I will do some kind of survey of these type of results from that have appeared now over since 2003, one can say, by various people. So I'll try to give you some overview of this. And what I think is still interesting with this is that you have a range of various possible scaling limits that can appear depending on certain choice of the relative speed of aggregation and time scaling. So I'll come to this in some detail. And one particular process that arises from this is what I like to call fractional Poisson motion, which is a relative to fractional Brownian motion. And I'll hope I can give you a feeling for this and where it comes from and properties and why it might be interesting. So a little bit on the background. So I said, lots of people seem to like to measure things, and they report evidence of heavy tails. It started early on in the 90s or even before that, but and also today there's recently something called Grid 5000. I don't know if anyone here knows about it. It's a French national grid system. Do you know about this, Francois? Yeah, it should be 5,000 nodes around France and all connected, and you can do design to make all kinds of interesting experiments. There's a paper now by Abry and others that they look at heavy tails in this traffic. So that looks interesting. There's a variety of explanatory models that have been suggested to somehow explain these observed patterns. Maybe the first one that was studied in some detail is on-off models, and a class of models I call here infinite source Poisson models, renewal type models. I will look at these in some detail and explain what they are, and the message. One message it will be that they behave pretty much in the same way when you look at them from a scaling point of view. So there's some unification here and certain patterns that I would like to I'll try to describe. Then one can ask what are really more realistic models for web traffic, say, or traffic in the wireless systems. Or it seems to be that most people like some kind of hierarchically structured model. And there are various examples of this in the literature now. You can find papers where they present 5 levels or four hierarchical levels. Here would be some web session level, would be where the users would be initiate these sessions. That could be typical infinite source Poisson type model there, as you will see a little bit later. Each level consists of a number of web pages that are initiated during this session. Perhaps that has an on-off structure. Each web page would consist of some objects depending on the application and so on. It could be, well, we would try to model this traffic structure during the on period, say, in the on-off character. And then when you come to the finest level, there would be packets during objects consisting of packets. So there are all kinds of variations on these patterns. Okay, so let's look a little bit on these generic classes of models. And the typical approach is to use heavy tails as one part of the input in these models. What is an infinite source Poisson? Well, think of the MG infinity model. So you have Poisson arrivals over a time scale. You have each arrival is a job of a certain duration with some distribution G. And what you do is to integrate this. So this describes the sessions over time, and the overlap of sessions are the sessions that are active at a certain point in time. And when you integrate this, you get a workload quantity.
What means integration?
Sorry?
What means integrate, to integrate?
Integrate over an observation window over time. So you have this is time. Here you have your Poisson arrivals. Each arrival is a job of a certain duration. And say that you integrate the number of active sources here over time. That's a measure of the workload in the system. So we'll see when we come to this, some details, you will see how it works. Then to make this a heavy tail infinite source Poisson, take the service time distribution to have a heavy tail called gamma here between 1 and 2. So typically in this talk, heavy tail indices will be called denoted gamma. On-off model, that would be rather an alternating renewal process type. So you have, maybe we could, this is this mg infinity. There's a parameter lambda here for the Poisson arrivals, that is the intensity of the traffic. In the on-off model, one would take sources that are either on during certain periods of time or off, and then you take the sum of these sources. This will correspond to the mg infinity process, and then you integrate this from time 0 to t. So this source will contribute a certain amount of work to the between time 0 and t, say, and you sum up number of users. And again, this is a kind of workload quantity. So that's what I mean by integrate over time when alternating renewal processes. Again, you make this heavy tail by playing with the distributions of the on and the off periods. Renewal type models, very similar. You just take renewal counting processes instead and think of this as a packet arrival model. So come back to this in just a few minutes. A little bit on the origin of these heavy tails. Well, what I'm discussing here would be some a priori modeling, heavy tail modeling, where you assume that these quantities in the models have heavy tails. That's the service time, the job duration, say. There are a number of papers where you look for some sort of ubiquitous outcome of another mechanism within the systems that would cause heavy tails. There were some work a few years ago where people were looking at TCP, for example, well, intrinsic effects of protocol mechanism. That would be that they could perhaps somehow create these patterns. Retransmit is an interesting mechanism that I will show you an example from. What I will discuss would be randomized service rates. So let's look at some of these. Let's see. Yeah. So the question here is: can you obtain heavy tails from short tails? The retransmit protocol is somehow suggests that you can. And there's some recent work, some of our colleagues on these, Søren Asmussen, and independently, I believe, Jelenkovic and Tan a few years ago. And there are several papers by Søren now. So here's an attempt to explain how you can get heavy tails from short tails. So think of a task of a length, random length L, exponential size, exponential mu. This is supposed to be transmitted on a link, but there are disruptions on this communication. Link that occur according to a Poisson lambda process. So everything is, there's just a Poisson process and one exponential sized object here. Problem is that if we need to find a gap in the Poisson process so that we can manage to transmit the whole job of length L. So as soon as there is a Poisson arrival during when we try to attempt, it's aborted and we have preempted and we have to start again. That's a retransmit mechanism. So how many times do we have to run this until we have carried out the job successfully? Well, I call this number m. Probability that you need more than n such attempts is a geometric quantity. So it's if you have more than n, you have failed n times to do the task. Failing is 1 minus the success probability. Success probability must be e to the minus lambda L, where L is the random size. But if you check if L is exponential, and this e to the minus lambda L is actually a beta distributed quantity. Do you see here? So the expected value is this number with against the derivative of this, or against the density of this random variable, which is delta x, it should be gamma x, gamma minus 1 there, where gamma is the ratio of these two exponential random variables that we have, the L and the Poisson inter-arrival time. But then you see, just by looking at this integral, this is actually 1 over n to the gamma, basically. So you have a heavy tail quantity here arising from this Poisson structure. So that's an example. It's nothing mystical with that. And if you take gamma between 1 and 2, which we could do here, we have an example of a finite mean infinite variance quantity. So this is something similar now I'm trying to build into an infinite source Poisson process. So let's...
It means no second moment, yeah?
And that's what I mean here, yes. I think it does so through this talk, yes. So let's take another short tail model, MM infinity. So now we have Poisson arrivals, we have exponential service times, and we just run this. Like over here, now these session lengths here are exponential, but not exponential with a constant intensity. But I want to play with them with a random intensity. It's called Xi. So this is a process that runs over time, and I will take this to be a stationary solution of this stochastic differential equation, which you recognize here as a type of what is called CIR process, often from its application in finance. Koch, Ingersoll, Ross, I think. But of course it's from a diffusion point of view, it's a standard Feller type diffusion with the diffusion coefficient, which is of the square root type, and the mean reverting drift. So here I put the gamma as the mean, as you see in this diffusion. So the x is attracted to gamma, and then there is another parameter called delta, which is something else here. So it's both in the drift and the variance, as you see. Gamma greater than 1, delta positive. For this choice of variables, it's known that this equation, the CIR equation, has a unique, well-defined solution, which is positive, and it has a steady state solution, which is gamma distributed. So for each t, if you run this, I think of having run this indefinitely into the past, we get xi. So for each t, it has a gamma distributed level. The parameter small gamma now is the shape parameter, and the scale parameter is 1. So mean and variance is gamma, for example. So it confirms that it really hits has its mean around gamma, and but it's of course it's a dependency, and the covariance is exponential decaying in this way, and that's where the delta variable comes in. As you see, it doesn't show up in the mean level, but it comes in the dependence. So in the financial application, this is used to model the interest rate, and then one can have a bond that depends on this rate, and you can derive a pricing formula for this bond, etc. It's also used in some biology situations as a random evolutionary rate, say. So it's this application I'm trying here is similar. I want to use this Xi process now as the exponential service rate. And what happens? Well, we have, if you call this V Xi, it's the service time of a job arriving at time t. So when a job arrives now, at time t, so this job, for example, it comes in here. Then you look at the diffusion process and see, okay, here the value is Xi of t, so it will get a service time which is exponential Xi t. This one comes at a later time, Xi t2. They will give its service time exponential Xi t2. So there will be a dependence, a correlation between these jobs now in this way. That's modulated through the.
You can just assume that the rate is gamma distributed.
I assume that the rate follows the station
yeah,
at the CIR.
You can just say that follows the gamma distribution.
Well, yes, no.
The CIR has non-shifted chi-square distribution.
Yes, but I'm not saying that. I want to use the dependence. I want to use the dependence. As two jobs that arrive close to each other should be more dependent than two jobs that arrive far apart.
I don't understand the terminology. You mean this is the system time of the job? Because jobs are exponentially distributed, right? I understood that the service rate was changing over time.
Yes, service rate is changing.
But so the job, when a job arrives, it has like an exponential distribution, and which is exhausted at this speed psi. That's the model.
Exponentially distributed with this rate psi of t.
So it's not
So
not
the-
like a random environment. It's you sample from a distribution.
Yes, I sample from this diffusion process. I have to know what time it is. I pick this rate right now. Maybe it's confusing, but I used rate for exponential rate, the service intensity.
So this is the parameter
Yes,
of the
yes.
job arriving at
Yes.
time t, which is following this.
Exactly.
No. I think the parameter at time t of all jobs who are present, service rate of all jobs who are
No,
present at this time.
no, you get it. You get your
No, I got
rate.
different. That's what I
That was my question.
Yeah, okay. You get your service rate at arrival. So it's not changing over time.
It's random. In this sense, it's a random environment.
Yeah,
No,
maybe.
it's not.
No, because it's changed at time. You're right.
I'm not sure about the
No.
terminology. But okay, maybe if you look here, it's simpler. So the service time now, probability that the service time is greater than v is, because it's an exponential with this rate xi t, is this quantity, which is the generating function of the gamma distribution. So so the service time has a Pareto distribution at each time. So of course that's what I wanted to achieve. So I was looking for some choice of psi that would be gamma, and then it's natural to pick this CIR, I think.
So what is the connection with the restart?
It's just restart was more to a simpler example where you can see that short tails give heavy tails, and I think this is a similar mechanism. It's not that you have to redo something, but
Okay, but it means that during a short time, actually, you will sample many jobs according. So that there is a similarity in the sense of
Yeah.
how the intuitively retails build.
yes.
Right?
Yeah, one should not draw too much on this parallel with retransmit. I will just more for this talk. Okay, again take gamma between 1 and 2, and we have this what I call heavy tail, finite mean infinite variance quantity. Now I want to do an infinite source Poisson process based on this infinity model. What does it mean? Well, given this rate, now we can take a Poisson point measure that runs on top of this diffusion process. And I'm just constructing an infinite source Poisson model in this standard way. So Nxi is a Poisson measure on R plus with this intensity. Here you see the lambda ds is for arrivals. This is the exponential density for the duration of the sessions. So the stationary, the M infinity model, the modulated M infinity is this. So you check how many sessions are active at time y. So that's what I had on the blackboard there. How many do you count at a certain time? Here's the integration to get the infinite source Poisson. You integrate over an observation window between 0 and t, and you get this quantity, which is the infinite source Poisson model. The standard infinite source Poisson model would be that to have, instead of this thing here, just a distribution for the durations of the sessions. So now I'm sort of running this thing on top of the diffusion. So as I said, I don't have too much results on this model, but at least one can check what is the mean and what is the variance and covariance, and it will tell us something about the structure here. So the mean is as it should be. It shouldn't depend on the diffusion. Should be constant, as it is here. T, linear function of t. And the variance has two components. One here that we want because it's the usual one, or close to the usual one. This is what you will get typically in the ordinary heavy-tailed infinite source Poisson process. It's proportional to lambda to the Poisson arrival intensity, and it has a certain form here. But then in this case there is also something that depends on the correlation, and the correlation coefficient shows up at one place here, delta. and it has a lambda squared form. So it's
Divided by T doesn't have a limit. The W divided by T doesn't have a limit.
this.
Natural limit.
Do you mean this
W
W thing
by
here?
T.
This is an increasing process. This
Divided by T.
yes, this is well increased. No, it's not increasing. This is the. Oh wait a minute. This is increasing. This is just you integrate over longer time. So something positive. So this is the workload as it aggregates over time, as it accumulates over time. In a little while we will center this and look at the fluctuations, and then we'll have some limits. The variance again. So here was the correlation shows up at one place, and there's some complicated expression here which is lambda squared. But at least we can see that if I take delta to infinity, what does that mean? This means that we take the correlation in the diffusion process weaker and weaker. You take so we kill the correlation in this way by taking delta to infinity, and then we get the only this first part. And if you look at this a little bit, you will see that essentially this grows like t to the 3 minus gamma. Or if gamma is bigger than 2, it grows like linearly in t. So one can check what happens to this, and of course it's the interesting case, for me at least, is the gamma in between 1 and 2. So we are in this heavy-tailed regime, and you will see that we have a variance which grows faster than linearly.
Gamma is equal to 3 halves, it's the maximum, yeah?
And gamma is equal to 1, close to 1 is
Oh,
maximum.
3 halves gives you the minimum speed, the minimum. 3 minus gamma equals 1 gamma, no, 1.
1. So it's either linear or faster than that. If I take delta to 0, this is letting the correlation be stronger and stronger. So now we have more and more dependence between the jobs.
No, again, it turns back.
What?
Turn back, previous slide.
Previous.
So maximum of t and t to the power 3 minus gamma, when power at t is the first, it's always 1. Okay. I'm sorry.
Gamma.
I'm wrong.
Gamma. I'm not sure if I said gamma between 1 and 2. Yeah. Okay.
Good.
Take now the correlation to 0. This means that we make the jobs more and more. Well, I shouldn't say correlation to 0. Take this parameter delta to 0. The correlation goes to 1. So the jobs get more and more strongly correlated in this way. Then what happens? Well, if you check here, you will see that this thing goes to 0 here. We get an integral that can check its final, but you need now gamma greater than 2. So something happens here, and we need. So if you need some more moments on the diffusion, or you get process here, and in that case we have a quadratic growth of this quantity. So it means that the workload is really a random variable times t, basically. So it's something. Everything gets just clumps together, and you get a workload. So. So much about this model, and I want to go on and look. Okay, what is it possible to take this gamma greater than 2 and still get some sort of power law behavior of this quantity? But let's go back now to the general area and see what is known and what type of results are known here. So asymptotic results for these a priori heavy-tailed models now. So now we will assume at the start of the input that we have a heavy tail. So the picture is that if we want to increase the aggregation level in the infinite source Poisson process, this means increasing the Poisson arrival rate. So we have more and more jobs. At the same time, I want to speed up time or scale time. appropriately and look at the fluctuations in this system. What kind of fluctuations do we have? Well, some text here. It depends on the relative speed of aggregation and time. As an attempt to explain, fast growth of aggregation relative time. This means if you take this model here, aggregation level would be the number of sources that we add up. So if this m is large in comparison to the time scale, we look at this, say the on-off processes. Or you can let the time scale dominate and have the m be a little bit smaller in comparison, and that would be a slow growth relative time. In these two cases, it's known that you see either, typically you see either strongly dependent paths, Gaussian processes, you see fractional Brownian motion typically. In the other case, slow growth relative time, you see independent increments, Livy, stable Livy, that sort of process. Then I'm interested in what's in between these two, some sort of intermediate regime or balanced growth relative time. And then something happens, we get the limit process, which has some other nice properties. More exactly what happens, say we have one of these processes, xt, continuous time, finite mean, stationary increments to keep things a bit simpler. Take IID copies, like we did in the on-off case here. It should have some long-range dependence property, or let's say it has a heavy tail index would have been better to put in directly. To see what the fluctuations are, subtract the mean and look at scaling in m and over time. I want to have the time scale go to infinity, I want to have the aggregation level go to infinity. Normalize this quantity and see what happens. So that's the idea here, to get a feeling for what kind of fluctuations we see in these systems. And there are basically three cases I see it. Fast, slow, and something in between. So I picked this heavy tail renewal process as an example to show what the theorem can look like. So this was the first model I worked on, and that's where I started to try to understand these quantities. So I take a renewal counting process. That's a usual renewal process with stationary increments, so it has a delayed first interval. Inter-renewal times, other than the first one, called U, finite mean, heavy-tailed in this sense of tail index between 1 and 2. So I fix a parameter to see. So here, and then you take many copies, independent copies of this counting process, sum them, subtract the mean, it's A t over mu. Look for some normalizing sequence. What can happen? Well, there are three things can happen, as I indicated, and here they are a little bit more directly written out. So here you have fast growth. Now the m grows faster than the aggregation grows faster than time in this particular sense here. This ratio goes to infinity. You take this sum, divide with something, normalize with something suitable, and you will get fractional Brownian motion with a certain tail index between 1/2 and 1. I'll remind you in a second what this is. This opposite case, if the time scaling is dominating in this sense, that a to the power gamma minus 1 goes to infinity faster than m, take the same quantity and normalize with something suitable in this case, which is basically am to 1 over gamma, you will see a stable Livy process. What happens if we try to stay in between these two? So you take this ratio and you let it converge to a finite number. For convenience, I call this number c to the gamma minus 1, basically, and then this renewal process, one should also take the mu there to simplify things a bit. It's more. You could have taken mu equal to 1 to skip this. The normalizing constant sequence in this case is A. and you will get a limit, well-defined limit, which is a scaled version of a process I call PHT. What are these limit processes? Well, the first one was fractional Brownian motion. So here, well, it has it's well defined for Hurst index that's called between 0 and 1. The H values that we get from this application are between 1/2 and 1, so it's heavy tail. So this is continuous Gaussian process, stationary increments, power law variance, covariance, consequently of this form. Stable Levy process is known, you know what that is, independent increments and so on. This other fractional Poisson motion, that I call it, it's this process. You take a Poisson measure with this intensity, ds on the arrivals axis, if you want, and the power log v to the minus gamma minus 1 on the duration axis. So this is a Poisson measure on r plus. Compensated the centered Poisson measure, integrate this particular function. Turns out that this has the same covariance structure as the fractional Brownian motion. And one can, at the time that we studied this model, we didn't know that that was one way to write the limit, but so we only knew at that time it was some process with some interesting properties, but I think this is the most natural way of looking at it. What does it have to do with fractional Brownian motion? Well, if you replace this centered Poisson measure here with a Gaussian measure, with this control measure, as it's called, you will get fractional Brownian motion. So it is closely related, although it's not so directly visible here. So now I claim that this is a generic pattern that we see here. Exactly the same result holds for infinite source Poisson processes. So here we have now it's finally written out a little bit what this infinite source Poisson is. Here we have the Poisson measure with some intensity, arrivals of the Poisson process, lambda ds, session length v, so f, distribution of the session length f v dv, integrate in this way. This is the infinite source Poisson process. Scale time with a. We don't have an m. We don't. The aggregation level is lambda now, so the aggregation level is hidden in here in the intensity. Find some b, suitable b, as in the previous model, and take lambda and a to infinity. 3 cases, you get fractional Brownian motion, stable Levy process, and this other fractional Poisson motion in between. So it's exactly the same, and this is has been obtained in some series of papers by Mikos, Resnick, Stegeman, 2003. They looked at the 2 fast and the slow growth case. Same result holds for on-off models as well. So now we have these 3 generic type models, all very similar, although they are not so similar when you start to look at it as I see it. So here ij would be this type of indicator function, which is 1 if the session j is on and 0 if it's off. Mu on, mu off are sort of descriptive notions, mean of on and off periods. Integrate, that's what we did over there to get the workload. Well, first we should sum to get the aggregation level, sum m levels and then integrate, normalize, exactly the same structure as before. You get three cases again, fractional Brownian motion, stable Levy, and the fractional Poisson motion. The intermediate case here is a recent result with Clément Dombry. But what I think is a bit interesting is that this is exactly a parallel kind of result for these models. So what about this intermediate limit process? Well, here's a bridging. It acts like a bridge between fractional Brownian motion and stable Levy in a certain way. And here's try to explain. So recall that in our intermediate limit we had the aggregation level and the time scaling together, so that the ratio converges to some number that I call c to the gamma minus 1. Then the limit process could be written c times the fractional Poisson motion at time t over c. Take c to infinity now, so that should correspond to this fast growth. Indeed, if I renormalize a little bit again, I will get fractional Brownian motion from this. As c goes to infinity, I should go in the other direction to get a stable, sort of make it less rigid, less dependence, kill the dependence between increments gradually. And if I multiply now by some power of c, I indeed get the stable Levy process. So it's really you can go back and forth in between these two.
You also get weak convergence in the appropriate topology.
In this case, you do. You get weak convergence.
Where you have FDD there.
Where I have FDD, I have actually a continuous process here, and a stable and discontinuous one. I say I cannot have tightness in the usual sense.
Well, not in the usual spherical topology, but in some of the other.
Yeah,
spherical.
yeah. Right. I was a bit discouraged by these things, but I'm sure it should be, if you are interested. I was more interested, to see that it actually works out in the distributions here, but there are finer things to add to this, yes. There's another property of this fractional Poisson motion. Let's see, what did I, just a second. Yes. This is maybe another way to explain this bridging, or what kind of process this is, and why maybe it has some interesting features. We'll call this aggregate similarities. So this process is not self-similar. You can check easily by just looking at the distribution. It's not self-similar like the two others. Fractional Brownian motion is self-similar with the index h. Stable Levy is self-similar with the index 1 over gamma, right? This in between is not self-similar, but it has this property. So if you can find a sequence of the scaling number c that goes to infinity. So when you trace through this process here that we got, this limit process, you will go through all the aggregates. You will go through all sums of the original process, IID copies of the original process. It's like it's similar not to itself but to its aggregates. That's what I mean. It's similar to these quantities. If you pick these C's properly. So you will go through all the sums. If you take C in the other direction to 0, then what? Well, you can find another sequence to 0, so that if you construct these fractions of the fractional Poisson process and sum up, you will get the original one. So it goes in the other direction. So you will get the C directly from this that's infinitely divisible, for example. So this is more an observation. I'm not sure if it can be used to something particular, but well, it's a nice property, I think. So these approximations now that we have tried to show here, what do they say about traffic if you want to use this as an approximation to describe network traffic? If we accept these crude models as they are, well, if I call a generic version of these three cases here, W, M, A, T. So this would be the workload, the sum of M of these copies, say, or at time AT. So we look at this at some aggregation level, some time scale. And then I look at this choice I did, which was that M divided by A to the gamma minus 1 would be constant. So my constant is C here. Then we see that if we take the workload and maybe compare it to, as I did in this display here, with AM, maybe that's natural. The AM would be what the capacity that you need to handle this workload without losses. So if you compare this to on a time scale A and aggregation level M, then you have some mean rate traffic, plus the fluctuations that could be maybe used to see, okay, what will we hit the end of the buffer or something like that. That should be described by this fluctuating quantity here. And it's just 1 over M times this random process. If we compare to the other ones, I play with this C once more and take it large or small to see what we could write it in this way. So that it's the mean rate plus some fluctuations that are fractional Brownian and, well, some size of this fractional Brownian motion, or stability and some size of it. Or if you prefer to write this in terms of original M and A parameters, aggregation and time, it would look like this. So it says something about the typical fluctuations that you will see in your systems. One feeling I have when I look at these measurements papers, I mean, there will be next week, I think there will be experts on this here, if not already in this room. When they do measure things in this system, I'm not sure if they, to me it would be natural to sort of identify the aggregation level and the time scale and then measure, but I don't think people do that. They measure something else. So it's I have no empirical use of this for the moment, but at least I wanted to show this. Of course, all this that I talked about here goes back, it has a history. Today it's called appropriately, I think, Taco's theorem. The original paper or papers were from around 95, Taco, Sherman, Willinger and others. So what they did at that time already was to center and normalize the workload for heavy tail on-off processes. So they looked at this on-off case in particular. And what they did was to take sequential limits. So first you take M to infinity, the number of sources, and then after that you take another limit in distribution over time, and then they saw this fractional Brownian motion appearing. Or if you change the order of limits, if you take time limit first and then the aggregation, you get a stability process. So this was a nice way to, this kind of pedagogical way to do it, and of course everything else is sort of based on this insight from that result. I should just acknowledge that. See, is there anything now to say about this special model that I discussed, this CIR modulated model? Well, I'm afraid I shouldn't say anything today, but I will. Well, this at least one can say that if I have to recall here, so now this is the modulated workload. Delta was the correlation parameter in this particular model I tried to introduce. It had a mean, which we should subtract. It had a variance that we should try to understand, and in the simplest case, the variance is basically this. And one should get constant times fractional Brownian motion. So this would just confirm the usual case. So this corresponds to fast decay of the correlation, so it should not be involved. But what I'm really interested in, of course, is to see if one could play with this delta and get something else here. So I'm afraid it's a little bit too early to say something here. But that was the intention to introduce this special model that a few minutes left, so I could maybe also mention that we looked at this fractional Poisson motion also from other perspectives, not as a limit process from workload models only, but in itself. And the natural question is if it should deserve to be called fractional Poisson motion, it should be a version also in this case where you have a negative dependence, or you have some analog of the fractional Brownian motion for Hurst index between 0 and 1/2. And this is our candidate for this, or our proposal. So if you take an h between 0 and 1/2, so now I leave this workload for just a few minutes to say a few other things. Take h between 0 and 1/2. Pick a tail index, we can call it a tail index, gamma 1 minus 2h. This will be in 0, 1. Form this particular thing, where n is again a Poisson measure with this intensity, just parallel to what we did. But now I'm integrating something special here. It's a difference of two indicator functions. And I cannot see directly why to do this, but it comes from a certain connection. And it turns out that this, if you look at the covariance, for example, of this quantity, it really is the one we would like to have. It is the covariance of the fractional Brownian motion. And what is the marginal distribution? Well, it's what I call symmetrized Poisson. If you take two independent Poisson variables and take the difference, two independent Poisson with this mean. So you have so this is really a discrete process. It's a birth and death process actually. It has jumps of size 1. The case h equal to 1/2, it would be the difference of two Poisson processes. That's a natural case to take. That would correspond to the Brownian motion. And finally, there is a version also fractional Poisson motion in RD in high dimensions. And there's just some formulas here to show that at least I claim that there are. In this case, h between 1/2 and 1, this is the heavy tail case. You recognize this almost. This is what I have discussed here now. Today there was dimension 1. In the high dimension, one can do something similar and obtain a process which is an analog of the Levy fractional Brownian motion in RD. So you get the right covariance for it. And the other case for h small, 2 1/2, very similar to what I discussed in dimension 1. You just make a similar construction based on a centered Poisson measure. So this is a little bit about that and ongoing work. Well, there are other examples, also things you can get in related processes, but maybe this is enough. So I think I'll stop here. Thank you very much.
What do you see as the best way to simulate fractional Poisson on computer?
Well, I would just do it as the infinite source Poisson process. I would take the durations of sessions and just overlap and add them together. I don't think it's very effective from a computational point of view, but at least it's natural from this point of view. So I only done some simulations for as visualization, but not for.
Property
that you showed that the process is not so similar, but sums again. Is that related to self-decomposability? You know what I mean?
Yeah.
I can't remember now.
No. Maybe I understand self-decomposability too badly, but I cannot see that it's very close. But
Functional level.
yes, yes.
I mean,
Uh,
I have to look my definition.
Maybe you can explain to me. I'm not sure. So.
Other questions?
Thank you.